We have just established what is called a Center of Excellence on Geobiology in Bergen. And this Center of Excellence, they are big programs that last for 10 years. And we are now, you can read this, but it's like our goal is to better understand, in an integrated effort, the interplay between the geology and biology. And we are focused mostly on the mid-ocean ridges system. We are geologists, geochemists. I am a geochemist myself. I have a PhD in physics, but I'm doing mostly physical chemistry on geological problems. We are micro and macro biologists and molecular biologists. And right now we are around 30 or more working regularly at the center. And we have also 10 or more associated researchers. And maybe we have at least one of them here. It's all. I'm not sure.
I'm not sure either.
Well, first some points on this. The title is Hydrogen-Driven Deep Biosphere. And the hydrogen is a powerful reductant. And hydrogen can form simple organic molecules by reacting with different carbon sources. Hydrogen is a substrate for chemolith autotrophs. These are kind of facts. It's a list of facts. Yesterday, 2 days ago, I got an email from researchers that told me that my presentation today is kind of rather provocative. Is the words used. He didn't agree with this hydrogen-driven biosphere. But I will show you that most of these things that we see, they are facts, some observations. And I have added some controversial or...
Can I ask,
Sure.
So what is chemolith?
Or chemo stands for the energy source. Litho is the electron donor, inorganic. Chemo means that it's inorganic chemical energy. Litho means that it is inorganic electron donor. Auto means that it's inorganic carbon source. And troughs means ethers, doesn't it? Yeah. Well, I have put on some yellow blobs in my presentation today, anything that is controversial today, or that can provoke some people. So then you can separate between what I will call facts and what will be a kind of controversial stuff. Hydrogen is evidence for water-rock interactions. We can observe along the mid-ocean ridges high concentrations of methane and hydrogen, and we take this as evidence for water-rock interactions in the subsurface. And I will explain all these points eventually. Strongly exothermic reactions produce hydrogen and drive hydrothermal fields where a magmatic heat source is absent. I could put a yellow blob behind this one because it's not established yet if the exothermic reactions solely can create instability and convection cells. Now, this is a slide I found, or a figure I found in microbiology from Nielsen et al. And they define these hydrogen-driven ecosystems and something they call slimes. And these slimes are defined as the subsurface lithoautotrophic microbial ecosystems. And this is one of the reasons why some people believe that these hydrogen-driven ecosystems are provocative or controversial. It's a misunderstanding, because the definition of these slimes is that these ecosystems are completely isolated from anything that has to do with photosynthesis. And what you see is that in the seafloor we have quite a lot of evidence for hydrogen-driven biosphere, but we can't really say that it's isolated from any photosynthetic products. So what I talk about here is a system that is not isolated from photosynthetic products like sulfate.
Not necessarily.
Not necessarily. It's really hard to prove that such slides exist. You can do laboratory experiments where you cut out everything that has to do with photosynthesis. The problem is that one of the definitions of these slides are that they are going to sustain and maintain life for a long time. And your laboratory experiment may last for 1 year or 1.5 years. It doesn't really prove that you can have a system working for 1 million years without any photosynthetic treatment. Now to the deep biosphere. The deep biosphere can be defined as geologically powered dark ecosystems. And again, I could put a yellow blob here because if you call it a dark ecosystem, then again you go into this discussion about the slime, that it's isolated from anything that has to do with photosynthesis. But again, my definition, at least for today, is that a system that is mainly driven by inorganic processes in the deep, with some input from photosynthetic products during these convection cells. The deep biosphere exists wherever geochemical energy is available. And there is a really important point, and that is that you have to have some kind of metastable redox gradient. You can't have an equilibrium system and have a deep biosphere. And I will show later that these redox gradients can form. Now, the last point is again controversial. Such ecosystems may set the stage for early Earth development and search for extraterrestrial life. It's not 100% agreement that this deep biosphere system can really be used as a precursor for life. I will start with saying something about where we have the energy to drive the hydrothermal systems. It's called what is a dissipative system. Then I will move on to field evidence and observations of hydrogen production. I will show you a couple of sites, of hydrothermal sites or vent sites along the mid-Atlantic ridge, and some new discovered fields in the north of Iceland. We look at, I will present some observations from ancient rocks or ophiolitic rocks. We have evidence from ODP, Ocean Drilling Project, and it's evidence from laboratory experimental work. Then we can put all these observations into numerical models and also produce data on how much hydrogen it can form within a given system. I will show you some examples of chemolitho autotrophs, and then at the end some controversial slides about the emergence of life in hydrothermal systems. Radioactive potassium, uranium, and thorium in the core and in the mantle is responsible for a large heat production. It's in the, I don't have a number, but it's in the order of terawatts. And this heat production drives convection cells in the mantle, and ultimately it drives what we call plate tectonics. It's the moving plate, or the moving lithosphere plates on the surface of the because of this plate tectonic, we have what we call divergent plate boundaries, and these are a picture illustration of the global system of mid-ocean ridges or divergent plate boundaries. And here we have a color illustrations of the age of the seafloor that has been created. What we see here is the red colors are young seafloor, and the blue colors are the ancient or the oldest part of the seafloor. And what we can see here is that these are a narrow red line here and a broad narrow line here, which shows that the spreading rate on this part, which is called the East Pacific rise, is much higher than the mid-Atlantic ridge. I will show you some hydrothermal fields from the mid-Atlantic ridge here, and also some from the Arctic ridges and the ridges north of Iceland. What is important to notice is that a slow to ultra-slow ridge, like is in the north, on the mid-Atlantic ridge, or in the south, might be dominated by tectonic activity, and that is that it is very little heat production or magmatic activity. It's not so much magma chambers, for example, beneath the mid-ocean ridges. And it's an important point. Now, along such a ridge, you have you could have, like in the East Pacific rise, you would have a magma chamber, or at least a heat source. And the heat will create a lower density upper space that will start to migrate upwards, and you will create convection cells. In this sketch, you can see that the typical seafloor is layered from gabbros at the base over the mantle peridiotites. It's got a sheet dike system. It's got pillow lavas on the top, and over there is sediments. And I will show you some examples of hydrothermal systems. One of them, which is close to the ridge, driven by a magmatic source, so it's got a large heat input, and then a different system that is some way away from the mid-ocean ridge, with a much lower heat input. Now, this is the kind of features that we can find on the seafloor. This is a black smoker, and a black smoker is in principle acidic solutions that contain some high sulfide concentrations, and these sulfide concentrations precipitate as soon as they are mixed into the seawater, and this is creating this black kind of smoke thing. I will show you two examples of these hydrothermal fields. This is the typical black smoker. The other one is, we don't see this black smoke because it's alkaline and doesn't have these sulfides. What is typical for these solutions is that you have these convection cells with seawater, then again reacting with the mafic and ultramafic rocks. You produce hydrogen and methane. You might have a methane source and a CO2 source from the mantle or from the magma chambers, and you can produce hydrogen by the interactions with the very reduced rocks. And this is what we usually observe before we find any hydrothermal system. It's a plume that lies above the hydrothermal system of reduced components. Now, the driving mechanism for the deep biosphere is that reduced species from the deep, and then I mean the rocks, mix with more oxidized species through convection cells. And because of these different states, you get this metastable redox couples. And again, this metastable is highlighted because you wouldn't have any biosphere if everything was at equilibrium. The microbes need to affect this. They need to have some chemical energy for their metabolism, and this is brought by this metastable redox state. To know how much hydrogen form and to what rate, we can do different things. We can observe reactions by observing the minerals, water gas chemistry, and microbial populations along these mid-ocean ridges, or the hydrothermal systems along the mid-ocean ridges. We can look at petrographic observations in the drill cores and ultraviolets. I will show you examples of all this. We can do laboratory gas, water, rock experiments, and we can do numerical simulations. When it comes to the direct observations of the hydrogen, we can look at directly at the hydrothermal vent sites, and it's two types that can be distinguished. It's sites that are driven by magmatic heat, like the black smoker that I showed a picture of. This is more complex, but for now it's okay. And it's a colder sites that are driven by exothermic geochemical reactions. Of course, you have anything between. In these sites, you have the exothermic geochemical reactions. And in most of these colder sites, you have some kind of heat input. So it's a gradual. This is a picture showing hydrothermal vent sites on a more on a global scale. And the red lobes here are what is found as active sites.
Did you make this map?
No, I'm sorry I didn't put a reference, but I googled.
Okay.
It's nice. You have quite a lot of these active sites. Did you make it?
No. I needed one.
And then you have some sites that are unconfirmed. And those are typically sites where you have some what is called a CTD. If you have the seafloor and ship, then you can lower a bottle that collects water samples, and you can find this kind of reduced clouds above a hydrothermal field. And this is what we are doing in the north now. We try to find hydrothermal fields, and usually we do this sampling of the water column, and we find this hydrothermal plume. It's very hard to find this small hydrothermal system. But anyway, when we find this cloud, we know that it's there. These are background values. These are values of hydrogen and methane that are much higher than the ocean.
I to understand that the regions that are marked are the ones that have been investigated, and for the rest we don't know. No, on the map. So why are there no vents in the southern Atlantic?
Oh, it is. It's just that it's a pain to go down in the south of Africa and do some kind of submarine investigations. It's really harsh conditions there, and it's much easier for us up north and just go out in the mid-Atlantic region and north. I think the density of these hydrothermal plumes are as large in the south as in the north, just that we didn't investigate them. Actually, we sent our researchers down to south of South Africa recently, but that was for some other reason, and we didn't really look for the hydrothermal fields yet. But it takes a cruise like 3 months or something just to go down there and back. So it's kind of, and we might get the ship for 1 month each year. So you have to have some kind of South African scientists to go down there and do the work.
Yes.
Now to examples of these hydrothermal fields, and the rainbow hydrothermal field is a typical black smoker type of system. It has a very high hydrogen concentration, up to 16 millimole per kilo water. It has a somewhat lower methane concentration of about 2.5 millimolar. It got a high iron concentration because it got a low pH. So the low pH allowed the high iron concentration. The rainbow is here, and Sweden is here. Now, this is some of the samples from the rainbow, and it shows chloride with a millimolar, and it shows one point here, which is the seawater concentration, and you see that all other measurements fall along a mixing line. The same with methane, which is also millimolar, and hydrogen. So everything falls between a mixing line between the end member hydrothermal solution and the seawater. And this means that it's probably only one source of this hydrothermal solution. This is some of the organics in the rainbow field. It's up to C29, and this looks great if we assume that they are synthesized in the rainbow field, but we can't say anything about this. We know that it could be, and it's probably mostly derived from organics in the sediments and these migrating convective cells. It hasn't been proved that you can form these heavier hydrocarbons in these hydrothermal fields. Now, this other more special type of hydrothermal chimney, they are white and consist of carbonates. This is the Lost City hydrothermal field, which is situated slightly south of the rainbow, and it is 15 kilometers from the mid-ocean ridge in a 1.5 million year old crust. Instead of the acidic solution that is emitted at the rainbow, it got highly alkaline solutions up to pH 11. Instead of the 3 to 400 degrees Celsius solutions at the rainbow, it's 40 to 75 degrees typical. But they have the similar range of methane and hydrogen, so this is a completely different system. This is probably to a much larger extent driven by these exothermic reactions in what we call ultramafic rocks, and to a lesser extent driven by a magmatic source. Now to the work that I'm a part of in the north. This is Iceland. Here you have this Jan Mayen fracture zone. And during our summer 2001 and BOD 2005 project, we found one active field north of Jan Mayen. Now we have found this is a field. So we have 2 or 3 different sites in this area which are hydrothermal active. And they look much more like the Lost City type of field. In the last cruise, 2007, we went to this area. And again we found quite a lot of these plumes, but no hydrothermal field. So we went around there for 1 month, fishing and fishing for this hydrothermal field, and it moved around. So you had kind of, we made a grid of, where we had like a positive, so this is kind of, you look down into the ocean, and with ocean ridges like there, and at one time we could find some kind of positive response there with a high hydrogen or methane. The next day it was gone. Then we found some points here, next day it was gone. So just what we figured out after 1 month is that the currents are constantly changing in this area. So it is a hydrothermal field there. It's very hard to say when the plume moves like this, and then 2 hours later it moves like this, and then it moves around. So it's not so easy to find these hydrothermal fields.
So if you go closer to the bottom, then it's even harder to find, you mean?
Yeah. These can stretch for like 10 kilometers or more. These plumes. What we believe is that here is that it's a very low magmatic activity, and what we probably will find is that we find I'll show you the concentrations. Remember I told you about this Lost City and Rainbow. We have up to millimolar concentrations of hydrogen and methane. What we see in these fields in the north is more in the range of micromolar. And we have up to 50 micromolar hydrogen and not significantly larger methane. That means that it's possible that these are partly ultramafic hosted, but can also be basalt hosted. So this could be a mixture of both. And this higher methane and hydrogen can't tell us very much because the methane stays in the water column for some time, whereas the hydrogen is broken down pretty fast. But we believe that it's also a magmatic source for the methane here. But so far we didn't find the system, so keep looking. We will have
The lower bump is the second plume down there?
that's the second plume. So we have 3 plumes there. This one only showed methane, no hydrogen.
So is the source the same, or you don't know?
Now it might be 2 different sources. This is an example of partly serpentinized ultramafic rocks. What you see here is this rock consisted in the start of pyroxene, autopyroxene, clinopyroxene, and olivine. And what we see here is that magnetite has formed in part. We have formed quite a lot of this chrysotile or other serpentinite minerals. And we have some olivine, relict olivine left there still. We have brucite and other hydroxides in fractures. And these kind of observations are kind of important when you try to simulate these systems. Because what we see is that it's a reaction front. Not all of the rock is in contact with the aqueous solutions at the same time. And when we do, or when if I talk on the behalf of typical people, mineralogists that do kinetic simulations, we assume that the reactive surface area is proportional to the mass of the rock. Then we assume that all this area inside the rock is also reactive. This is wrong. So we usually overestimate the reactivity of the rock greatly. And this is something that we will work on to add these spatial dimensions to our kinetic simulations. Another evidence is from ocean drilling projects. They have quite a detailed information on the composition of the seafloor and the rocks. Here we can see a gradual decrease in the amount of olivine and pyroxenes, and you start forming these secondary minerals, the same type that we saw in the firelight. Chrysotile, brucite, magnetite typically form. You also see that you can separate between a rock-dominated system and a fluid-dominated system. In a fluid-dominated system, you have a much larger water-rock ratio, or much more water going through the same volume of rock. I think this laboratory experimental work is great, because then you can directly read in your laboratory how mantle rock, or a peridotite in this case, dissolve and produce hydrogen. In this case, Seyfried Jr. and the other co-workers dissolved this peridotite that consisted of autopyroxene, clinopyroxene, and olivine at 200 degrees Celsius over 800 hours, which is close to a year. And this is after the reactions, and you can see most of this green stuff is serpentinite. Then you have some olivine. Some of this brown stuff is brucite, and you have some magnetite. What they see in their experiment is that they reach after more than half of the experiment, they reach hydrogen concentrations of up to close to 250 millimolar, which is pretty high. They also did some what I would call semi-kinetic simulations, where they have a reaction rate on the minerals that dissolve, whereas the precipitates are calculated at equilibrium. You can see here that it's a overestimation of the hydrogen produced by the simulation. And I believe personally that one of the reasons is that they overestimate the surface reaction area. The other one is not only that, it's also that some of the iron, ferrous iron, was not oxidized. It was incorporated in brucite and these other minerals. So the amount of hydrogen that formed is proportional to how much ferrous iron that is oxidized. And they kind of missed this in their simulation. Later, they changed the parameters, but they don't show this graph. Now, just to show you more like how hydrogen forms when these minerals dissolve. Here's an example of this is olivine, and this X is the amount of iron, ferrous iron or reduced iron in the olivine. So the dissolution of olivine consume H+, so you get a more basic solution, and produces ferrous iron, magnesium, silica, and water. And this the amount of ferrous iron is typically between, for these rocks, between 0.15 and 0.2. I have some samples with called Foster-Wright 91, with this X is 0.18. As soon as this ferrous iron is in the aqueous solutions, might be oxidized by oxygen to form ferric iron. And this is a general equations for also incorporation of ferrous iron into serpentinites or chrysotile, and ferro and brucite and magnetite. So this ferrous iron is consumed and it's oxidized, so you remove one important point here is this oxygen is consumed. And the reason why hydrogen is produced is because of the reduction of water. This precipitation of the minerals is a driving force for reducing more, for oxidizing more ferrous iron. But it's not producing hydrogen. The hydrogen is produced by the reduction of water. This is because water has a stability field for a given redox potential or a given pH. And water is stable within a region of the redox potential, and then it will be unstable. What happens is that if we consume the oxygen, we go down on this scale and we can get into this area where water is unstable. Then water will react to form hydrogen and oxygen, and you will move up to this line. So whenever you are in this region and you produce this ferrous iron and oxidize it, you will go along this lower line of the water stability. And this is what produces the hydrogen. More oxygen is consumed by more ferrous iron, so you get this situation that you jump under this line and produce hydrogen to increase the oxygen again up to this line. So we always go along this stability line. Now, just to show you some numerical simulations, I've done 3 different types of simulations, and each has kind of it's a reason to do every kind of simulations. And the first one is equilibrium consideration, and the 2 others are with some kinetic reactants. I have used an example of this olivine, this Foster-Wright 91, and precipitation of brucite, magnetite, and chrysotile. And then it's the pure end member, magnesium, chrysotile, and brucite. Equilibrium approach is nice if you want to understand chemical changes and you assume that everything is in equilibrium. And in many cases, this gives a good estimate of how much hydrogen is formed, given a degree of rock transformation, or said in a different way, if you titrate in or add such and such amount of olivine, then you can expect that this and this much hydrogen will form, given a complete equilibrium reaction. The limitation is that it lacks a time dimension, so you don't know how fast this happens. Now here's one example where I have an initial rock volume of 5 liters, which with a 20% porosity, that means that you have 1 liter of water, and then you have 30% olivine and 50% of a non-reactive mineral. Altogether, this gives a total of around 30 moles of olivine, which is more than 1.5 kilo or something, with olivine dissolved into this liter of water. It's more, it's a couple of kilos of olivine, so it's quite a lot. What we do is that we titrate this in. So at the x-axis, we see the moles or amount of olivine added, and the given change in the brucite, magnetite, and chrysotile at equilibrium with the solution, and water. What we see is that water is consumed because of this reaction. So all the time, water is transformed into hydrogen and oxygen, which again, oxygen is consumed by the ferrous iron oxidation. And we form chrysotile, brucite, and magnetite at some given proportions. You can see that after just a small addition of olivine, completely dissolved, oxygen falls down to 10 to the minus 40 to 10 to the minus 60 in the extreme case, and hydrogen is produced. We see that the ferric iron is reduced, the amount is reduced, I mean, and the ferrous iron increase in amount. In this case, in this extreme case, without looking at the solubility of hydrogen, we can produce 2,000 millimolar of hydrogen. This is not reasonable. It would be a phase split, and this hydrogen would kind of migrate out.
Just relating this back to the plumes, do you have oxygenated water down there? Do you have lots of oxygen in the water that's anoxic?
Where? In the
plumes?
In the plumes, it's reduced.
It's reduced, so you have it's no oxygen, or
it is oxygen, but it's a very low oxygen.
But they still survive those plumes.
Yeah. Well, these plumes are metastable. It means that they are not in equilibrium. And even if you mix them with some seawater, you will see that hydrogen will still persist for some time. So it will become some kind of metastable plume. Same with manganese, and in the case of these acidic plumes, you will also see ferrous iron in the plumes.
So, where on this graph are you normally? Are you close to the threshold line in these near these hydrothermal vents, or to the very right of this plot?
No, I would think that we are well within this region.
Yeah, so constantly
Yeah.
in your used state, yes.
It doesn't say anything about the actual concentrations here. The plumes are a mixture of these vent fluids and ocean water. But the plume is slowly reduced, the plume water.
I see, of course, yeah.
Now,
and you would be, I mean, to the left you would only be if you were in about the atmosphere near the surface. Yeah.
Now to the semi-kinetic and kinetic approaches. I define semi-kinetic as a model where you pretend things to be kinetic. That is, that you choose some part of the system, like the dissolving minerals, to be constrained by reaction rates, and then you say that everything else, like precipitates, are in equilibrium. So some half-away kinetic system. And then you have the full kinetic approaches, where every mineral phase and every known metastability is constrained by reaction kinetics. These type of simulation are used to understand these systems constrained on both thermodynamics and reaction rates. And the benefit is that, first of all, that you get the time dependence included. And of course, in most systems, you will also see that doing a kinetic approach, the system will not stay at equilibrium. You will have phases that are forced to stay off equilibrium, which is important. Limitations: it's hard to upscale rates from laboratory to field scale. This reactive surface area is a much debated entity. It's much simplified in these simulations, and in real it's complicated. The replacement reactions is hard to model without adding spatial dimensions. And this is what we saw in this case. To do a correct kinetic simulations of this system, we should at least add 2 spatial dimensions. It's one more complicating factor with a kinetic approach. In the equilibrium approach, it's very simple to solve numerically. You solve for each kind of phase you have, for each element. You solve one nonlinear equation. So you have a system of nonlinear equations to solve. In this case, it was 10 nonlinear equations, which was solved very rapidly with some Newton-Raphson algorithm. In the kinetic approach, you have almost the same number of nonlinear equations, and then you have to add a very tough system of stiff ordinary differential equations. And this is the reason, I think, why most people avoid this kind of simulations. It takes a long time to simulate. Well, I've seen cases where you almost simulate the same time as you simulate 1 hour in 1 hour. It's kind of useless. In this simulation, this is the semi-kinetic approach. I assume that olivine is constrained by reaction rate, whereas the other minerals are at equilibrium. In this case, I added the phosphorite 91, and we see that in 1 year it dissolves, completely dissolves. And what happens is the precipitates is in this case in the same kind of relative amounts that in the equilibrium case. But now you have a time dimension. If we look at the aqueous solution, we can, given the initial solution, give a time when all the oxygen is when the oxygen is consumed and you start producing hydrogen. And in this case, we started with the same amount of material, and we end up at the same high hydrogen concentration. Now we have a timing of the element. I didn't show the complete full kinetic simulation, and I simulated for a couple of days ago, so it was kind of hard to make a stable simulation because of this stiff nature of the problem. You don't know if you know what a stiff system of differential equations are, but it starts getting fluctuating and it's hard to solve numerically. Anyway, I compare my kinetic simulations with semi-kinetic simulations, and we see that it's virtually no difference there. So I would do these kind of full kinetic simulations just to check and compare with a semi-kinetic approach. And then if it's okay, I would use a simpler approach like a semi-kinetic approach for a full-scale simulation. There's no need to run a hard-to-solve full kinetic simulations if it will give the same result as a semi-kinetic.
So when you're in a steady state, then of course they are the same. Exactly.
Yeah. Now to the metabolism. Evidence of that hydrogen is used as an electron donor. And it's quite a few examples of this. We have microbes that do. I was thinking about that this table is not really 100% correct. I did some discussions with some colleagues in Bergen, and it says that photosynthesis is dependent, and it says that this anaerobic methane oxidation, by reducing the sulfate, is photosynthesis independent, and we don't believe it is. You wouldn't have enough sulfate in the system without the photosynthesis. You would have sulfate in the system, but not enough for this reaction to occur. Anyway, it's quite a lot of other mechanism that is hydrogen dependent. You can reduce carbon dioxide by hydrogen, again sulfate, sulfide, nitrate, and so on. More in detail, it's quite a lot of these archaea and bacteria that is now mapped to utilize hydrogen as an energy source. And this is, for example, the reduction of sulfite to H2S, sulfate to H2S, sulfate to H2S again, and so on. And what we see is that the hydrogen is consumed in several steps here. In this case, you have enzymes that reduce from sulfate to sulfate to H2S, consuming hydrogen as an energy source. And these are so it's well established that this kind of hydrogen-driven biosphere occur. What is not established is how it is isolated from the photosynthesis or not. Now to a more provocative heading, the emergence of life via hydrothermal systems. This is debated. Some people believe that life formed first in a hydrothermal system. Some people feel that this is has to be wrong, but it couldn't be the case. But what we see is like the evidence, or not evidence, but what supports a life that formed in a hydrothermal system is, for example, that the formation of small organic molecules between through reactions between hydrogen, CO2, carbon monoxide, and etc. And this has been shown experimentally by McCollum and Seward. These are short-changed hydrocarbons. They have shown that they can produce organic acids experimentally in these reactions. It's a Fischer-Tropsch type of reaction in an aqueous phase. It has been shown by Amanda Schock, by thermodynamic considerations, that you can form all 20 of the amino acids that's needed. And this is not a surprise now. It's pretty easy to make amino acids, it seems. So, you have sharp redox pH gradients that is held at a metastable state in these hydrothermal systems. I think this is a demand for the development of life. You have to have sharp redox pH gradients, and you have to be able to hold them at a metastable state. You have inorganic catalysts like magnetite, iron, nickel oxides, and so on. And you have temperature that vary. It can be up to 400 degrees down to seawater temperatures. I don't know if you know Mike Russell, but Mike Russell has some kind of complete theory of the formation of life. It's controversial. And in his system, he claims that he has to have this kind of off-axis hydrothermal system that is not this black smoky type, more like the Lost City type of color he produces is alkaline. He assumed that the ancient ocean is acidic, it was acidic, because of a high CO2 partial pressure in the atmosphere. As soon as these serpentinized aqueous solutions meet the seawater, in his model, he precipitates some iron sulfide bubbles, which creates a membrane between the reduced alkaline hydrothermal solution and the seawater. And this is, in his model, some kind of semi-permeable membrane. And this kind of system, I will not go into detail here, he compared with a cell membrane in bacteria. He put in all kinds of the same kind of iron, nickel, sulfide compounds that are in the enzymes and so on. And he can concentrate these organics inside this bubble and polymerize organics. And it's a lot of missing links in his, or not missing links. He got everything there, but it's not verified. So I think that is what is missing in this model. Is a lot of things that is not verified. It's assumed that this and this can happen. But it's a complete model. And he's not the only one with these complete models. It exists several others. And they are usually in some kind of hydrothermal setting where you have all these kind of favorable settings. To summarize, dissipation of energy from the Earth's interior is necessary for life. And I put a yellow blob behind this one because I told someone in my department, a microbiologist, this, and I told him that without a dissipated Earth, or without the convection cells and without plate tectonics, the Earth will die. And I told him this will happen. And he was kind of provoked by this and told me that he expects that life can continue without plate tectonics and without any heat from the interior of the Earth. I believe that the Earth will die, and that is why I put a yellow blob there. You have sharp metastable redox gradients that provide energy for a deep biosphere. Hydrogen is produced from the reduction of water, where reduced elements like ferrous iron, manganese are provided. The local hydrogen concentration is dependent on hydrodynamic condition as well as the rock substrate. So, depending on what you dissolve and how much water is going through, you have different hydrogen concentrations. Hydrogen is a strong reductant and provides energy for a large range of microbes, and this is a fact. Hydrogen was abundant at the surface of the pre-oxytic Earth. And the last controversy is hydrogen was necessary for the onset of life. This is not established. This is kind of discussed topic.
Thank you very much. Questions, please. This was actually one of the answers you gave me when I was asking about Monique Rosing's model, where, of course, the amount of oxidized iron is dependent in his model on the photosynthesis. And so you are saying now, of course, and that's probably well known perhaps, that of course it's really done by this reaction. So I wonder what Monique would say against this. You see what I mean? I mean, Monique is using photosynthesis to explain the oxidized iron.
You would have oxygen as long as you reduce water, and then you will, as long as you have this ferrous iron and you oxidize it,
and so
you will always have water enough to produce oxygen again to oxidize more ferrous iron.
Exactly, and so his argument really doesn't have any basis, then, according to this.
I think so, but I have to read his paper.
I'm not sure. It's all of the rates of reaction, of course.
The what?
Reaction rates?
No? But this is measured, or?
Well, it is.
Yes.
I mean, if you try to dissolve olivine into water in an oxytic environment, you will produce hydrogen. And
yes, I mean, what rate is the question then, perhaps? I mean, is that perhaps it's hardly imaginable that this is a limiting factor, right? Yeah, at what rate does it happen? Does it depend on?
Suggested this reaction is controlled by the dissolution rate of the olivine in this case.
Yes. Okay.
And then you assume that the consumption or the oxidation of ferrous iron is faster than the dissolution rate of olivine.
Mm-hmm.
And as long as it's faster, then it's controlled by the slowest reaction, which is the dissolution of the olivine.
I see. Maybe
And then you also assume that the reduction of water is either instant or faster than the oxidation of ferrous iron.
Mm-hmm. Yes.
But this can be tested, of course.
Mm.
Well, I mean, Minik was aware of this, but he didn't take it into account because I don't know the reason for it.
Should
Yeah,
have Minik always around.
Yeah, so your first conclusion or summary, you showed that dissipation of energy in the interior could be important for the origin of life. But you implied now in your summing up that actually you're also thinking about
Yeah,
The current,
okay, when you look at Mars,
Mm.
for example, no plate tectonics, no fresh material to the surface. And I think that is one of the reasons why you kill off everything that could be life there. Because you need a fresh surface. Everything will move towards equilibrium in different rates. You will have some kind of metastability, but with time, even a metastable reaction will proceed towards equilibrium, but slowly. So eventually, you will approach equilibrium on such a surface where you don't have any fresh material. And there's no reason to believe that you will have life if you have no kind of redox gradient. You could form some redox gradient by some kind of photosynthesis or something. I believe it. Well, it's possible to do some simulations on this, I guess. To simulate a simple system where you can include the photosynthesis and and a given amount of fresh surface, and then see what happens.
Mm-hmm.
The real world is kind of dynamic, but when you second factor, of course, that you turn off the electromagnetic field. It's also bad for life. But you can have these kind of organisms living inside Chernobyl, so I mean, but I think they will also eventually die.
But you're saying that what's happening on the ocean floor is important for the whole Earth
Oh yeah, sure.
right now.
Yeah.
Is there any idea whether Mars, when it was 500 million years old, may have had? People do believe that there was water and oceans, but there was maybe even then no plate tectonics. Yeah.
But you didn't have any continents. And
That's right,
you
yes.
had some kind of
What?
There wasn't
That
geological
was-
activity.
well, yeah, of course.
Actually, there is even now, of course, every now and then.
No, I mean geological activity. You can say that
First
the
like-
complexion cells in the osmosis is geological.
no plate tectonics.
No plates.
Yes. Yes.
But the complexion cells.
It's an interesting remark because when often nowadays one sees these animated pictures of Mars with the deeper valleys being drawn in blue, as if it was full of water, right? And now you say, of course, there was no continent, which is true.
Well, at one
These pictures are highly misleading somehow.
Well, at one point you had some plate tectonics on Mars, right?
Some type of.
Yeah.
I mean, there's a big, right?
Is really the last
Right
line
now.
controversial? Hydrogen was necessary for supply.
I think it is for some.
Some.
That's why I
I think
did it
it's
as yellow
always
blog, because
controversial.
for me it's not controversial for me, but I mean, I start getting these emails from angry Russians. I put it as a yellow blog there.
Okay.
I mean, I think in all models that are at least concentrated on the development of life on Earth, then hydrogen is a necessary part. Now it's argued that panspermia and stuff, and I don't think hydrogen is a part of the panspermia theory. Is it?
No. You mentioned, you said the surface area relative to the volume gives an overestimate or underestimate or something like this. But this depends on the reference value, right?
What you do in a laboratory is that you crush
Yes.
your olivine
Yes.
to a fine powder.
Uh-huh.
And that means that when you put this fine powder into your beaker and dissolve it, almost the whole olivine will be in contact with the solution.
Mm-hmm. Uh-huh.
And from there, and then you have some kind of, you have an estimate of this reactive surface area of the olivine with some gas absorption on the powder. So you know that given a mass of olivine, you will have a reactive surface area and a reaction rate. And then
yes.
you normalize your reaction rates to this surface area.
Right.
The problem is that when you have a large piece of rock and only the surface of the rock is exposed to water, there is no longer any correspondence between the reactive surface area and the mass. And this is what happens in the real
You
life.
underestimate the surface.
Yeah.
Yes.
No, you overestimate
Why?
the surface area when you try to simulate the real world.
You overestimate. Yes, yes. You think it's too much. Yes. Yes. That's because you didn't crush the whole thing anymore.
Yeah.
Right.
But this is possible to do something about if you add this spatial dimension. Instead of you doing it in a Fortran code or whatever, you can do it in console and add some spatial dimensions, and you have a reaction front and replacements and everything. And this is like the next step. And try to.
There was
Then
this
you,
one
from
yeah.
this type of console simulation, so we add a spatial dimension.
Yes.
You can kind of scale
Yes.
back to your reactive surface area based on a spatial model. And then you can get the other reactions right. It's the
Maybe you should
reactive
show us this
surface
picture
area.
again. That was interesting, I thought. Yes.
So you see, you have some kind of reaction front.
Yes.
Whereas in the lower,
Is that actually this or this? This is here, I don't
you
know.
see here, I think this was the boundary.
Yeah.
Then you have a boundary here,
Uh-huh.
formed by the magnetite.
Right.
Some kind of olivine
Yes.
boundary.
Yes.
And this part is mostly not in connected. Doesn't really dissolve at all.
Yes.
Before this reaction point has reached.
Yes.
So with this kind of, you have an aquaspace. If you have an aquaspace here, and you have some other minerals here, these minerals are heavily fractured because it's less dense than the olivine. So you will have some kind of fracture network, which would have lead to some migration of fluids. But anyway, so you have some diffusion of liquids in here through the solid minerals or through the fractures, which will lead to eventually that all the olivine is replaced by the new minerals.
Yes. And that's some kind of, I mean, the diffusion is, what's it called? Following Dawson's law for diffusion, perhaps, right? It's not a diffusion which goes proportional with the Laplacian of the...
No, these are very tiny
concentration.
fractures. I mean, it wouldn't be just a simple expression of the concentration difference. It would be also a function of the width of the fractures and so on.
Yes.
I guess.
Yeah. Locally dependent, yes. That's interesting. Right. Okay, if there's no further questions, then let's thank Helge again.